Okay, good evening, everybody. Let me share my screen in the first place. All right, so now it's being shared. And now I'm going to switch to presentation mode. All right. Well, so thank you for inviting me to give this talk. I'm Álvaro García López from University Rey Juan Carlos in Madrid, Spain, and I'm going to prove to you that the wave-particle duality comes from classical electrodynamics, that we can explain this phenomenon without appealing to anything else than Maxwell's classical electrodynamics. So let's begin. In the first place, I would like to give some justification to the present work. And one of the reasons that spurred me to research in the foundations of quantum mechanics is that in general, in quantum mechanics, we do not know why things work as they do. We don't really know the mechanisms that explain the quantum physical phenomena. We don't know the underlying behavior that explains, for example, that particles can experience interference effects, diffraction, for instance, and so on. So the thing is, to understand this phenomena, we really need models. And I like to say that quantum mechanics is like some sort of calculator, because most people know how to use it, how to follow the recipe and compute things. We all remember from Mermin that shut up and compute. So it's in the end a computer, but most people, at least not many of us, know why it works the way it does, how it works inside, what's inside a calculator. So for that, you need models, and this was very clearly explained in a seminal paper by David Bohm in 1952, where he proposes a hidden variable theory. We will refer to this work later on when we derive the quantum potential from classical electrodynamics. But one of the sentences you can find in that work is the statement that there is no real models in quantum mechanics, one-to-one correspondence between physical reality and the system, but we only have a statistical correspondence. So how can we say that this is all that there is? So in the present work, I'm going to show that the wave-particle duality can be explained thanks to a nonlinear dynamical oscillation, which is called a self-oscillation. Okay, so this is the crucial concept which I think explains the wave-particle duality. Another motivation to embark on this journey is the discovery of experimental discovery of working droplets. As we all know, these are fluid models in which you can have a silicon oil drop bouncing on a bath. The bath is also made of silicon fluid, but it is vibrating, and there is when the droplet hits the water, it produces waves, and these waves affect the way that the particle bounces and moves horizontally, and there is a feedback. So you see, it's sometimes said that in quantum mechanics, particles behave as waves, and some other times they behave as particles. And this paradigmatic example is when you have a double-slit experiment. And in a double-slit experiment, you know, when the particle goes through one of the slits, which we cannot figure out which one it is, because we destroy the interference pattern, behaves as a wave. But then it is told to us that this wave, one of a sudden, disappears and concentrates at one point in the screen where the particle is located. Well, here, as we can see from the modeling of droplet, of droplets, if the particle has a pilot wave attached to it, then the particle can interact with itself in a double slit experiment. The phenomenon of walking droplets was discovered, among many other researchers, by Yves Coudert, who died a few years ago. And what I would like to say is that interphenomena, I mean the fact that the particle goes through one of the two slits, cannot be empirically studied in quantum mechanics. This is true because you disrupt the physical process if you try to find out through which slit the particle went through. But that does not mean that it cannot be modeled, and a more accurate modeling can be new verifiable phenomena with it. I mean, the assumption in quantum mechanics that we already know everything that can be known from a system, it also assumes that we already know all the experiments that can be done on a system, and that's not true. I mean, the experiments you are, in some sense, allowed to do depends also on your theoretical frameworks. So I would like just to recall that we can model this kind of phenomenon. There are empirical models right now and also theoretical models. So pilot waves coming from fluid dynamics is a second reason to study the origins of quantum behavior. And finally, I would like to recall what I call the paradox of a structure. And it is usually assumed that electrons or fundamental particles have no structure. In this sense, they must be regarded as some point mass. And the problem is that points, they don't have internal structure. And I wonder how particles not having internal structure can have internal properties, if we assume at least that the wave function has a probabilistic interpretation. So, I mean, where do internal properties come if there's an internal structure? I mean, what's the difference between 2 points? If I show you 2 points and I say this is an electron and this is a muon, how do you tell the difference between them if there is no structure? So if on the other hand, here I would like to think particles have some kind of, probably not, field configurations, and the internal properties could be explained thanks to their structure. So two particles having different sizes, but same example, thinking of a knot geometry or topological configuration, they could have different mass if mass is related to rest energy. Okay, so in this way we can also give a foundation to many principles, because quantum mechanics is, there are lots of principles, because you cannot explain things, you have to state them in terms of principles. So you have lots of principles, and you can have quark confinement, asymptotic freedom, many things that perhaps could be easily explained if we assume that even fundamental particles have a structure. In this case, I'm thinking of the electron, which is the main concern of the presentation. But if particles have a structure and they are made from fields, which are the basic, the most fundamental concepts in modern field theories, then particles can self-interact. So I like to use this metaphor, also very similar to, or quite similar to the droplet, walking droplets used in fluid dynamics. And if you have a person swimming in the pool and he hits the water, he gives a stroke with his right arm, for example, he produces a wave. But then this wave affects the way he hits the water the next time, so there's a feedback. There's a feedback phenomenon between the waves that the particle produces and the motion of the particle, which then affects the way the new waves are produced. So there's a problem of self-interactions, okay, and which lead to feedback phenomena. Here we are going to show that there are self-forces as a consequence of particles being extended, and these produce time-delayed interactions. And we are going to show that these time-delay interactions produce self-oscillations, a jittery motion, and we are going to derive Zeta-Bewegung frequency for a classical electron, but extended electron. So this is mainly our model. I mean, we are not going to put any ingredients, no hypothesis, no strange weird things. Use Maxwell's 19th century classical electrodynamics. So the Lagrangian density of Maxwell's equations with sources. So we are going to assume that there are particles do exist as sources of field, although in the end of the talk, I would like to suggest that particles themselves are field configurations. But for the moment, we are assuming this Lagrangian with two terms, the fields here, and the other term in the Lagrangian density is the coupling between the fields, of course, and the matter. This is the for potential, this is for current density, this is charge density, and this is current density in Euclidean space. Okay, so the solution to these equations are the retarded potentials. So this is the for potential, here is the scalar term, and this is the vectorial potential. And they are related to the densities through the by means of the currents, but the currents are time delayed because it is the motion of the currents in the past that determine at a certain point the potential at the present time. These two are derived in the Lorentz gauge, and if we work the for potential for a point particle, we obtain the very famous Liénard-Wiechert potentials, which depend on the speed relative to light speed, the charge, the distance. These were derived by in the end of the 19th century by Alfred Marie Liénard and Emil Wiechert, and you know these potentials. What I would like to, draw your attention to this fact. These potentials are time delayed, so they are retarded potentials, and these time delays are going to lead to a description of the motion of particles in terms of delayed differential equations. So we are not going to disregard these time delays because they are key to explain the phenomenon of self-oscillation. The model of the electron we are going to assume was devised by David Griffith, so it can be read, you can read about it in his book on classical electrodynamics, the introduction to electrodynamics. So it's a very simple model which consists of a rigid charge density. So we are going to have a charge density. We find 2-point particles. The extended body, I surrounded it here, but it's just made of 2-point particles at a fixed distance. So it's a rigid charge density. The distance between the particles is d. Each particle bears a charge of minus the charge of the electron divided by 2. So the total charge of the particle is the charge of the electron. And we are going to study just the transversal motion. Okay, here we are just interested. You can also study the longitudinal motion, but that one is dissipative, so purely or mostly dissipative. So I'm here just interested in transversal. So this as a whole is going to move in this direction. And the key idea is that when this body, if you want, this Dumbo with the 2-point particles accelerates in this direction, the upper part can emit a light perturbation, an electromagnetic wave, because or particles and charged particles, when accelerated, emit waves, just perturbations through the field. So the thing is that this particle can emit a perturbation, and the particle at the lower part of the body can absorb this perturbation later on, and this is going to produce a feedback phenomenon. Okay, so the idea is that a particle can here its voice from the past. So there is a self-interaction between the different parts of the particle, of course. The motion of this one also affects this one at a later time, and the arrangement is going to be symmetrical. All right. So you can compute using the Liénard-Wiechert potentials, the field created by one of the two particles comprising the body on the other, and then you can add up both of them to compute the total self-force exerted by the particle on itself. And this is what you get. This was already derived by David Griffiths in a paper in which he studies the possible electromagnetic origin of mass. And a very interesting thing is that we already find inertia here. This is very important. We don't need to put acceleration in Newton's laws, and this is going to be also a crucial idea. All right. So with the self-force, the first thing that one is tempted to do is what we have been educated for, is to just write down Newton's second law and use the self-force and solve this, if you can, solve this equation. And certainly you can do this. And if you do this, then you can also expand the delay term in the position of the body. And if you do that, you're going to obtain a Taylor series for in the delay. This is the time delay, or you see it all the time, and appearing to all orders. And well, you can do some algebra, and you can obtain the following equation. Since you expand in Taylor series, you get an infinite set of forces, and you find an infinite set of forces here. There are many nonlinear terms combining speed and acceleration. This is a very, very famous term, which is usually called the Lorentz-Abraham force, or the Abraham-Lorentz force. It is the first, beyond the inertia term, the first linear term with a higher derivative. This is the jerk, or the derivative of the acceleration. And but you could you would have to get all of them in the end. The thing is that the inertia term, which we already had mass, there is a term already coming from electrodynamics, which with a term of electromagnetic mass. So frequently it is considered that this leads to a renormalized mass of the electron. This would be the bare mechanical mass, and then you have the dress or renormalized mass would also have to take into account the electromagnetic mass of the particle. Okay, this is what it is. You can find this frequently in papers or things similar to it. But here I want you to change your mind, to forget about mechanical mass, because in the end, the most fundamental classical theory is electrodynamics. So if we already have mass coming from electrodynamics, why do we have to put mass? So do not assume Newton's second law and let it emerge from electromagnetism. We can obtain Newton's second law from mechanics. So this is a change, a conceptual change. So how do we write then the equation of motion? So here, the equation of motion, we can write it as it was many centuries ago, written by D'Alembert. D'Alembert used to, when you use the D'Alembert principle, or also the principle of virtual work, to develop these Lagrangian formulations of classical mechanics, D'Alembert proposes that the term of inertia should be posed as another force, what we would call a force of inertia, and just formulates the law of motion of dynamics as an equilibrium. This is what in general relativity you would call a geodesic equation, because it's like if you go to a reference frame of the moving body, and there is no acceleration, but you get forces of inertia. So here we are going to identify forces of inertia as, for example, the centrifugal force as a self-force of electrodynamic origin. If we do that, we can also use Sommerfeld relation, which connects the charge of a particle with the Planck's constant. And if you do that, I'm doing it because we are going to need this formula to derive the quantum potential later on. You obtain that mass is proportional to h bar, which is something you usually find in mechanics, wherever you find inertia or mass, you obtain Planck's constant. Okay, so the relation is given by the finite structure constant. And now in the appropriate limit, you can approximate the self-force as the mass of the electron by neglecting all the other higher order terms, times acceleration, and what you get is Newton's second law. So Newton's second law is not a fundamental law, but the whole science of mechanics is not a fundamental science, but it comes from electrodynamics. And this is very important because in the end, quantum mechanics, it's based on the Hamiltonian of classical mechanics. And also the Dirac equation, as we are going to show, is based on Einstein's mass-energy relation, which is not fundamental, can be derived from classical electromagnetism as well. Well, for the moment, we just want to study the motion of a free particle. It's not free because self-interacting, but we have no external forces, so the self-force is equal to 0. And if we do that, we obtain, with the equation from previous slides, the equation of a nonlinear oscillator. I have, in the Liénard-Wiechert potentials, this appears as retarded, all the variables are retarded, and this one is not retarded. I have advanced in time all the kinematic magnitudes so that you can read it more easily, this equation. Okay, so now it is an advanced differential equation, but this is the time delay in the end. And here you can see you already have Newton's term of inertia without introducing mechanical mass. You do not need mechanical mass. So this is the term of inertia. This is a term of dissipation, which is very similar to terms appearing in books of the theory of sound of Rayleigh, and also in the famous Balthasar van der Pol oscillator, you can find a term of dissipation, quite similar. It's not exactly the same, but not so different. There's also a term of elastic restoring force, which just shows that Hooke's law already comes from electrodynamics. And there's this new term I wanted to relate it to someone, and I decided to relate it to Michael McKee from Canada, because he proposed that in a book about the arrow of time, that the arrow of time might come from time delay differential equations. And this term, well, this is an advanced term, but it contains here the delay. And the amazing thing about this system, what makes it so complicated, is that you can demonstrate, I won't do it here with a bit of algebra, that the time delay depends, it's not constant time delay, because depending on how fast the particle moves, the self-signals come from earlier, past or later in the time. So there is a dependence of the time delay on the kinematical magnitudes, the speed of the particle, and the acceleration of the particle, and also the speed of the particle, the gamma factor. So, I mean, there is a kinematical relation between the time delay and the kinematics, right? So the particle is evolving, and depending on how it evolves, its light cone, it's evolving with it. And the self-signals coming from the past, that affect it in the present. If it goes faster, then they come from earlier times in the past. This is the idea. So this is why you find this type of relation. So this is a nonlinear delay differential equation, and it is a state-dependent delay differential equation. Very hard to, I mean, you cannot find, there do not exist even numerical schemes to solve this kind of equation right now. I'm developing them. So this is a typical equation of a nonlinear oscillator. I mean, whoever has seen a nonlinear oscillator, this is typical. So what we can do is we can linearize the previous equation and to study the stability analysis. So we are going to set the particle at rest, and what we do is we very weakly as weak as you want, perturbate it, and see if it returns to its equilibrium or if it keeps oscillating. And if you do that, if you study if you perform the Lyapunov stability analysis in the previous equation, you can find that if you put the particle at rest, you can find that the characteristic polynomial has zeros in the real positive part of the complex plane. So you see, this is a domain coloring function of this complex function. And where all the colors meet are just the eigenvalues. There is an infinite set of eigenvalues. Contrary to constant delayed differential equations here, the delay is in all the terms of inertia, speed, and that means that I have advanced the equation to study the stability, and this means that here you have an exponential, a growing exponential. That means that there is an infinite set of eigenvalues. So you have infinite eigenvalues, infinite eigenmodes of oscillation, and all have real positive value. What means that the rest motion and also any uniform motion I show in this work, that is unstable. So you put the particle at rest, you give it a little, and it starts to jiggle very, very fast, and you can obtain the frequency. And the frequency is related. There is a form factor, of course, depending on the shape of the particle, to Zeta-Bewegung appearing in Dirac's equation. So the idea is that particles are buzzing. Okay, and well, this is what we call a self-oscillation in the theory of nonlinear oscillations. There's a very important book on nonlinear oscillations by Alexander Andronov. Self-oscillation it can be defined as the production of a periodic motion using energy from an external source. Here, the particle is taking the energy from the fields outside, from its own field in this model. Although if you do the same analysis with other shapes, sometimes you need, I mean, you don't get instability. You obtain a Hopf bifurcation, and the trembling motion, the jittery motion, dissipates as time goes by. So perhaps you need already some fluctuations, some background fluctuations, but the phenomenon is the same. And now what you get is the thing is that the external source, you don't need it to tune. There is no need for resonance. I mean, the external source can have no periodicity, and through the mechanism of feedback through its own motion, the particle, the way it takes energy and releases energy, it's made through the particle's motion. So you don't need to, this is not a resonance phenomenon. You need to tune frequencies, okay? There's feedback here. So, the idea is that electrodynamic systems are open systems far from equilibrium. And here I recommend a very, very recommendable reading about with a very nice historical development, and also with key concepts concerning the thermodynamic structure of self-oscillator. And this work by Alejandro Jenkins in Physics Reports is very recommendable. So what we call this kind of dynamics limit cycle dynamics. There is a theorem by Liénard for fundamental oscillators where you have this kind of strange functions. You can extend this theorem to delayed differential equations if you want. And depending on the conditions you give to these functions, you can have, well, mainly two types of behavior. And the transition from one type of behavior to another is called a Hopf bifurcation. Here you have an stable limit cycle, which means that you kick the particle, it starts to cycle, to oscillate, to vibrate, but as time goes by, it suddenly dissipates and stops vibrating. But on the other hand, if all the conditions are fulfilled, you can put the particle at rest. You give it a very, very, very little perturbation. You blow on it, very little, and it quickly starts to grow in amplitude fluctuations until it attains a limit cycle behavior. So this is usually called damping. This is disordered entropy increase and decay to a state of rest. And this is the opposite phenomenon. It's called propulsion, order creation, and you can do it whenever the system is open and you can take energy from your environment. These are excitable. They are called excitable systems. Okay, in the theory of nonlinear dynamical systems, and also in chaos theory, if you want. So another very interesting thing is that because the particle is open and it's sending energy and also absorbing energy all the time, these systems are not invariant under time reversal. So you get dissipation from the first derivative in the oscillator. And in this sense, I like to see Zitterbewegung as nature's fundamental clock, sometimes, in some sense, the heart of time. And this is again Alejandro, and in his paper he shows that there are lots of systems, and that all these systems behave as natural clocks. Okay, they are adaptable, but they do not require a fine tuning. And they are self-excited. So metronomes, the heart, vortexes, heat engines. The cell cycle, even biogeochemical cycles in nature, most of cycles in nature, I would say that work through this nonlinear mechanism rather than being harmonic oscillators. One of the problems of fundamental physics is that it is based on the harmonic oscillator, and most oscillators in nature are non-harmonic. So also the clarinet reed works as a nonlinear oscillator. So these systems all have an arrow of time, which is due to the fact that the systems are open and eating energy, getting energy from the environment and releasing energy from the environment. Okay, and this is managed with their own motion. Well, finally, I would like to draw attention once again to David Bohm in his paper in 1952. In which he suggests an interpretation of quantum theory in terms of hidden variables. Well, he basically, what he does, it's not very complicated. He just he writes, following a work of Madelung in 1927, he writes the wave function in a polar form. Okay, and by doing this, he manages to write a system of coupled partial differential equations. Here I'm showing just one of them, and he shows that by doing that, R would be the modulus of the wave function, and the phase of the wave function would be S, except for a factor H bar, and shows that you can write the Schrödinger equation as a Hamilton-Jacobi equation, where you have to find out what he calls the quantum potential. And he draws, well, this paper is amazing for anybody who has read books on chaos theory, because the main key concepts of chaos theory, as for example, sensitivity to initial conditions, concepts such as Bayesian of attraction, channels, he calls them, you can find them all. I mean, in 1952, it is more than a decade before main results in chaos theory, such as Mel's Horseshoe, for example, were developed. Already the key ideas of chaos theory are already found in the paper of Bohm. They are, he uses another language, but the ideas are the same. The importance of fluctuations, in some sense, symmetry breaking. I think all those concepts, self-organization is already in some way in that paper. So it is very, very surprising to read Bohm's paper in 1952. It's very advanced for his time. So, which shows that very, very deep knowledge, in fact, of quantum formalism, in fact, which is, of course, expressed in his book on quantum mechanics, conventional Copenhagen interpretation of quantum mechanics. So the main conclusion of his work, I would say, is that the wave function is not just a probabilistic entity, but it is a real field. Okay, it produces forces. There's a quantum force here. There's a quantum potential and there's a quantum force. So then we have to ask ourselves, from a philosophical point of view, if quantum forces, as Bohm derives them, are a basic force of nature, so to speak, a fifth basic force, or if they emerge from other fundamental forces, electromagnetism, for instance. That's what I'm going to show. I'm going to show that you can obtain something like this with this constants, after all, from classical electrodynamics. So this I'm going to call the self-potential. So what we do to obtain that, we start with the non-dissipative part of the self-energy of the particle. Okay, and from that, you have to do a lot of algebra with series expansion, gather all the terms, make some integrals, but you have to use some previously shown relations. For example, the expression of the delayed in terms of kinematic variables. But if you do that, that's done in the paper. You can read it in the paper. You can express the unstable quantum potential you can derive a quantum potential from this self-energy. You only need to use the Liénard-Wiechert potentials and things we have shown before. And if you do that, you can obtain two terms. I mean, you can express this in terms of two things. The first one is the relativistic energy exact formula. You only need electromagnetic mass. You do not need anything else. Just assume electromagnetic mass, and what we have been saying, and just plain electromagnetic mass, and you get directly Einstein's relativistic energy. And this contains both rest mass or rest energy, but also kinetic energy, vis viva. So this means that this formula is not fundamental. You can derive it already from classical electrodynamics. And that means that mass is not fundamental. And this formula is the formula from which we derive, for example, Dirac's equation. So if mass is not fundamental and this formula can be derived from the Liénard-Wiechert potentials, then it is obvious that, I'm sorry, but Dirac's equation cannot be fundamental. Despite being the most beautiful equation in physics, it cannot be fundamental. But you also get another term, and this is totally new, something very unexpected. This just shows that we have been doing things properly. I mean, we have derived Einstein's. If Einstein's formula is accepted, our work derives it, so it is in accordance with Einstein's theory of special relativity. But you obtain one more term, and if you use electromagnetic mass, well, it's a very complicated potential. It is a non-conservative potential. It depends on acceleration. In fact, it should depend on time retardations, time delays. But what tells us that this is a quantum potential is that you have here h squared divided 2m, the same term that appears in the Schrödinger equation, just coming from electrodynamics. I mean, what does this mean otherwise? If this does not mean that the quantum forces are coming, quantum phenomena from electrodynamics. I mean, we would have to explain what this means anyway. Okay, so you can make an approximation, and if you approximate the motion, the oscillating vibrating particle motion by a linear harmonic oscillator, you can approximate the previous potential to this potential. This is already very well-known potential. We call it in nonlinear dynamical systems the Duffing potential, because it was devised by Duffing. In particles physics, they call it the Mexican hat or the Higgs potential. So the idea is that this potential has an unstable point here. This would show the instability of rest, and this would produce a symmetry breaking of the Lorentz group. All right, this explains the fact that the rest motion or uniform motion, which is unstable, so we are breaking some kind of symmetry, and this can be uniform motions in special relativity are related to the Lorentz group. So, but this depends on the geometry. For some other kinds of geometry, as you could turn the geometry from prolate to oblate, you can have a Hopf bifurcation. So perhaps in general, you might need some background fluctuations to destabilize, but you don't need to fine tune or to produce a resonant effect, as it is done in some other theories. Well, anyway, the idea is that uniform motion is destabilized, right? So this produces our phenomenon of symmetry breaking. Symmetry breaking is very important in fundamental physics. Not only in condensed matter physics, the Higgs mechanism was devised in the first place by Philip Anderson. Ilya Prigogine stated the importance of symmetry breaking through the study of bifurcation theory, and the oldest studies were given by Carl Jacobi, or already studying fluid dynamics. Okay. All right. So. Finally, it is frequently stated that according to Ernst Mach, the forces of inertia, for example, the centrifugal force, here you see when you have this bucket which is rotating, well, there are some candles in it, and when it rotates, these two weights lift due to the centrifugal forces. So it was stated by Ernst Mach that these forces of inertia are a consequence of the result of the affection of all the external bodies when the body is rotating, because in the reference system of the body, all the universe is rotating in the opposite direction. So he said that it was distant galaxies and all the matter around this body, which is lifting these weights. Well, so it's important to recall that these forces of inertia and the centrifugal force is not a pseudo. It's sometimes called pseudo force. No, it's a very real force. Okay, we see it here that produces real effects if the body is attached to the rotating body. Okay. It's a different situation when you just study the motion of a body that is not attached to this rotating body in a rotating reference system. Then you could call them pseudo forces, but not here when the body is attached. So, and the centrifugal force, our proposal is that it comes from the interior of the body. So, inertial forces are not due to inertia forces are the self force is an inertia a force of inertia. So inertial forces are not due to external distant bodies, but consist in an electromagnetic internal self force of self-induction. So this is Faraday's law. It's producing the self-induction, and this is Faraday's law causing the lift of the weights. And I would like to call this, because it was originally proposed by Domingo Soto, there was a force of resistance. Newton already calls mass times acceleration a force, and he calls it a force of resistance. He calls it a vis incita, already coming from the interior of the body. He knew it. And Galileo calls it resistenza interna. And also in Latin, Domingo Soto, you can read resistentia interna. So the main idea of the present work is that mass is not fundamental, right? That if you use natural units, in fact, you get that energy is mass. But the question is what type of energy. So in classical electrodynamics, energy is rest energy is electrostatic energy. So I like to recall what Wittgenstein in his Tractatus used to say, that all the densities are tautologies. And here the tautology is not one that relates many concepts, but in the end, if you use natural units, just two concepts in a direct way. So this means that we can do all the physics, we can do all the present work without talking about mass. We just define mass because it is comfortable, and we use this notion in all our daily lives. So it's in the markets, whenever we go to the supermarket. So it's embedded in our way of thinking it's rooted in a very elementary way. And in this sense, we always think that we need mass, but the point of the present work is that we define mass, and that we should not define mass and neither use it. It's a redundant concept in fundamental physics. So our theory of fundamental particles on fundamental physics should be done without saying anything about mass, because we do not need that concept, despite it's useful. But if mass is not fundamental, there is a corollary to that, And because the gravitational force comes from mass as a property, it's believed in the general in the law of general gravitation, the general law of gravitation, excuse me, then the gravitational field is not a fundamental force of nature. So it is usually say that there are 4 fundamental forces, and gravity is one of them, because bodies have mass. I say take this one out, not gravity. These two are already unified, so in fact we would have 2 types of Maxwellian fields. These are non-abelian Young-Mills fields, but in the end they are very similar to Maxwellian fields. So I'm inclined to think that if you consider space-time curvature and electrodynamics, you could already get these 2, but we will see. But anyway, what's gravity then? Because we see that bodies fall and we have a force of gravity, but then it would be a macroscopic residual electromagnetic field resulting from average radiative fields over great numbers of atoms, or perhaps not so many big number of atoms, but it would be a residual electromagnetic fields. So gravity is not fundamental. That's another proposal or a corollary of the present world. And finally, I'd like to end with the principle of equivalence. The principle of equivalence, we all know it, says that, there are different versions of it, but the most fundamental one, it says that, well, it explains why all bodies fall with the same acceleration in the Earth, and it's because inertial mass, the one appearing in Newton's second law, and gravitational mass, the one appearing in the general law of gravitation, are the same. And this was already explained by Einstein in terms of the principle of relativity, if you want, of general relativity, because you can always create a gravitational field by accelerating. So if you are in empty space and you accelerate in a rocket, then you are creating a gravitational field, right? So these 2 are equivalent. And on the other hand, if you are free falling towards Earth, in this reference system, objects are floating if they are falling as well. So there is an inertial reference frame, local inertial reference frame attached to this free falling body, which is commonly related to Riemann normal coordinates. Well, this free falling is true, but we have to be very careful, because here we must neglect what they are called tidal forces, because the gravity in the head of Einstein is not the same as in the foot. And generally we can neglect this difference in gravity because Einstein is very small compared to the scale of variation of the gravitational field. This is true. But otherwise Einstein would be deforming. But what happens when you have self-forces? You have tidal self-forces, and very strong self-forces. So here we would like to say that the principle of equivalence is good and works locally, but we have to be very careful, because it doesn't work as well if we also bring into account self-forces and extended objects in the end. And finally, we also like to draw attention to the fact that perhaps the reason why inertial mass and gravitational mass are the same is just because they are electromagnetic mass. So this is it. Thank you very much for your time and patience. Right now I'm inclined to think that particles already come from fields, and they are compactified structures in the field. If quantum phenomena can be explained in terms of electrodynamics, then I'm inclined to think that particles are some kind of electromagnetic solitons, electromagnetic knots, vortexes, some sort of field configurations, and I'm trying to find them in the Einstein-Maxwell equations, or perhaps we need to introduce nonlinear theories, already built-in nonlinear theories of electrodynamics or something else, but we need the principle of general covariance to ensure that all frames are possible, and we don't have then we don't need an ether and frame-dependent theories, absolute space-time in the end, which all our fundamental theories of particles rely quantum theories of particles rely on absolute space-time. So these are the two works where you can find more in great detail all the results here stated and more, and that's it. Goodbye.